Welcome to UXL, where you can learn new skills anytime and anywhere. Visit uxl.com to explore our full course selection. This lesson is part of a larger course. Check the video description below for a link to the full course where you can enroll. If you enjoy our content, please like and subscribe. For your convenience, the course cover displayed on your screen provides the complete course title and lesson title. Let's proceed with the lesson. Lesson: Key components of generative AI systems. Generative AI systems represent a transformative innovation in the field of artificial intelligence, enabling machines to generate new data, such as text, images, music, and more, that resembles a given dataset. These systems leverage complex algorithms and models to create outputs that are not mere replicas, but rather novel instances inspired by the training data. The key components of generative AI systems are fundamental to understanding how these systems operate and achieve their remarkable capabilities. This lesson will delve into these components, providing a detailed examination of their roles and significance. At the core of generative AI systems lies the generative model, which is responsible for producing new data samples. One of the most prominent types of generative models is the Generative Adversarial Network. Introduced by Ian Goodfellow and his colleagues in 2014, GANs consist of two neural networks, the generator and the discriminator. The generator creates new data samples, while the discriminator evaluates their authenticity by distinguishing between real and generated data. This adversarial process drives both networks to improve continuously, resulting in highly realistic synthetic data. For instance, GANs have been used to generate photorealistic images, such as human faces that do not exist in reality, which demonstrates their power and potential applications in various industries. Another critical generative model is the variational autoencoder, which combines principles from deep learning and probabilistic graphical models. VAEs consist of an encoder network that maps input data to a latent space and a decoder network that reconstructs the data from this latent space. The key innovation of VAEs is the introduction of a regularization term in the loss function, which ensures that the latent space has a well-defined structure. This structured latent space allows VAEs to generate new data samples by sampling from it and decoding the samples. VAEs have been successfully applied to tasks such as image generation, where they produce high-quality images by capturing the underlying distribution of the training data. Recurrent neural networks and their variants, such as long short-term memory networks and gated recurrent units, are essential components of generative AI systems for sequential data generation. These models are designed to handle temporal dependencies in data, making them suitable for tasks like text generation and music composition. RNNs process input sequences one element at a time, maintaining a hidden state that captures information about previous elements. LSTMs and GRUs enhance RNNs by incorporating gating mechanisms that regulate the flow of information, addressing the issue of vanishing gradients and enabling the modeling of long-range dependencies. For example, OpenAI's GPT-3, a state-of-the-art language model, utilizes a transformer architecture that builds on the principles of RNNs and attention mechanisms to generate coherent and contextually relevant text. The training process of generative AI systems is another crucial component that determines their performance and effectiveness. Training these systems involves optimizing the parameters of the generative model to minimize the discrepancy between the generated data and the real data. This optimization is typically achieved using gradient-based methods, such as stochastic gradient descent. However, training generative models can be challenging due to issues like mode collapse, where the generator produces limited diversity in the generated samples and instability in the adversarial training of GANs. Researchers have proposed various techniques to address these challenges, such as feature matching, mini-batch discrimination, and spectral normalization, which enhance the stability and diversity of the generated data. Data representation and pre-processing play a pivotal role in the success of generative AI systems. The quality and diversity of the training data directly impact the quality of the generated outputs. Pre-processing steps, such as normalization, augmentation, and encoding, ensure that the data is in a suitable format for the generative model. For instance, in image generation tasks, data augmentation techniques like random cropping, flipping, and rotation are commonly used to increase the diversity of the training data and improve the generalization ability of the model. Similarly, in text generation, tokenization and embedding methods are employed to convert text into numerical representations that can be processed by neural networks. Evaluation metrics are essential for assessing the performance of generative AI systems and ensuring the quality of the generated data. Commonly used metrics include the inception score and the Fréchet inception distance for image generation tasks. The inception score evaluates the quality and diversity of generated images by measuring the confidence of a pre-trained classifier in recognizing the generated samples. The Fréchet inception distance, on the other hand, compares the statistical similarity between the generated data and the real data in the feature space of a pre-trained network, providing a more comprehensive assessment of the generated data's quality. For text generation, metrics such as BLEU, Rouge, and perplexity are commonly used to evaluate the fluency, relevance, and diversity of the generated text. The ethical implications and societal impact of generative AI systems are also critical components that require careful consideration. The ability of these systems to create highly realistic synthetic data raises concerns about misuse, such as the generation of deepfakes, which can be used to spread misinformation and deceive people. Additionally, the biases present in the training data can be propagated and amplified by generative models, leading to biased and unfair outcomes. Researchers and practitioners must adopt ethical guidelines and implement fairness, accountability, and transparency measures to mitigate these risks and ensure the responsible use of generative AI technologies. In conclusion, the key components of generative AI systems, including generative models, training processes, data representation, evaluation metrics, and ethical considerations, are fundamental to understanding how these systems operate and achieve their capabilities. Advances in generative models, such as GANs, VAEs, and RNNs, have enabled the creation of highly realistic and diverse synthetic data. The training processes and data pre-processing techniques ensure the effectiveness and generalization ability of these models. Evaluation metrics provide a means to assess the quality of the generated outputs, while ethical considerations address the potential risks and societal impact of generative AI. As generative AI continues to evolve, mastering these components will be crucial for modern leaders to harness the potential of this transformative technology responsibly and effectively. This concludes the lesson. We trust you found this video informative and engaging. To enroll in the complete course, please use the link provided in the description below. At UExcel, we are committed to your learning journey. Each course offers a certificate of completion, online support, and downloadable resource files to enhance your experience. If you found our content valuable, we invite you to like this video and subscribe to our channel. Thank you for joining us, and we look forward to supporting your continued pursuit of knowledge.